Welcome to The Explainer. Today we're unpacking a topic that is literally hiding in plain sight, yet it quietly governs everything from your morning alarm to billions of dollars in international finance. We're talking about the hidden chaos of global timekeeping in software architecture. You might think time is just a simple number ticking upward, but right beneath the surface of our global networks, it's this fascinating, incredibly complex, and sometimes chaotic coordinate.
Okay, let's dive right into this. If I ask you, what time is it really? You'd probably just glance at your watch or your phone and give me a simple answer. But if you ask a database, a server, or a global app, the answer is incredibly complicated. Machines have to process time across physical server locations, user locations, ever-changing political rules, and even the literal rotation of the Earth. And if you get it wrong, well, the bugs can range from a mildly annoyed user missing a Zoom meeting to catastrophic financial audits.
So here's our roadmap for today. We'll cover the time zone trap, when microseconds cost millions, surviving the leap second, physical moments versus human intent, and finally, the golden rules of time.
Section 1. The time zone trap. Let's start with a classic baseline frustration that practically every software developer on the planet has faced at least once.
Picture this. A user over in Tokyo schedules a huge global online event for January 1st. Now, the database lazily stores the text 2025-01-01 with absolutely no time zone attached. Later on, a user in Toronto logs in, sees January 1st, and naturally assumes that means their local January 1st. But because Tokyo is 14 hours ahead, when that event actually kicks off in Japan, it's still December 31st in Canada. That Toronto user misses the event entirely, all because the software stored a date without its vital context.
It really boils down to this core idea. A date that makes perfect sense in one time zone might be totally incorrect in another. Storing dates or times without context isn't just some tiny logic error. It's a guaranteed recipe for confusing your users, losing their trust, and potentially causing real financial losses if we're talking about things like subscription renewals or exam deadlines.
Moving on to Section 2, when microseconds cost millions. Let's shift gears from basic user scheduling to the massive financial stakes of timekeeping in enterprise architectures.
100 microseconds. We're talking 1/10,000th of a single second. Under the European MiFID II regulations, trading venues and participants are legally required to synchronize their business clocks to within 100 microseconds of Coordinated Universal Time, or UTC. If you're doing high-frequency trading, your timestamps need a granularity of just 1 microsecond. The stakes here are entirely legal and financial. You absolutely have to be able to prove exactly when a trade happened.
So how on earth do you actually achieve that kind of precision? Well, your standard network uses NTP, the Network Time Protocol. It's software-based, gives you millisecond accuracy, and hey, it's perfectly fine for standard business reporting and regular web servers. But for high-frequency trading, you must upgrade to PTP, the Precision Time Protocol. PTP requires physical hardware timestamping. Think specialized network interface cards and a grandmaster clock sitting right on the network, just to bypass the variable latencies of a normal operating system.
Because without those perfectly synchronized hardware clocks, the whole system just falls apart. In an environment where thousands of trades happen in a single second, a 1 millisecond delay can mean a catastrophic financial loss. Sequence tracking fails, you can't reconstruct trades for your audits, and detecting market abuse becomes literally mathematically impossible.
Section 3. Surviving the leap second. Let's talk about bending time.
Now, we're zooming way out, from tiny microchips to the actual rotation of the Earth itself. Here's the crazy physics problem. UTC is based on incredibly precise atomic clocks, but the Earth rotation is slightly irregular, and it's generally slowing down over time. To keep our atomic clocks aligned with the physical position of the Sun, scientists occasionally add a leap second to UTC. But computers fundamentally hate a 61-second minute. When a system clock hits 23:59:60, operating systems completely freak out. We're talking duplicate timestamps, system hangs, and major kernel panics across global networks.
So, to fix this without literally crashing the internet, tech giants like Google rely on a technique they call the leap smear. They actually bend time by slowing down their servers by 11.6 parts per million. Here's how that standard smear actually works in practice. Instead of violently shoving an extra second into the clock all at once, they start at noon UTC. For the next 24 hours, the system clock just runs fractionally slower. Over the course of 86,400 seconds, that tiny slowdown perfectly absorbs the extra 1 second. By the following noon, the servers are gracefully realigned with true UTC.
and the system never had to process a terrifying 61st second.
But here's the thing. Smearing is basically lying about the true time for 24 hours, and regulators? Yeah, they don't love that. Because of this friction, there's a massive international push to just eliminate leap seconds entirely by 2035. Modern software engineering values continuous, predictable atomic seconds way more than strict astronomical alignment with the sun. Section 4. Physical moments versus human intent. This right here is the core philosophical breakthrough for software engineers.
There are two fundamentally different things you've got to consider when storing time. Category A is physical moments, things that already happened, like a server audit log or a financial transaction. These should always be stored in absolute UTC because their meaning is totally independent of location. Category B is human intent, like scheduling a future meeting or a deadline. This relies heavily on local rules and should always be stored as the local time plus the specific IANA time zone ID.
To see why storing that intent is so absolutely vital, just look at the time zone history of Egypt. They introduced daylight saving time in 1940, suspended it in 2011, brought it back in 2014, paused it specifically for Ramadan, abolished it in 2015, and then restored it again in 2023. If you took a user's future appointment in Cairo and just blindly converted it to UTC math, every single time the government changed the law, your stored UTC value would suddenly point to the wrong local time.
And that is exactly why this mantra is so critical. Store intent, not math. An IANA time zone identifier like Africa/Cairo or Europe/Vienna isn't just a static offset. It is a dynamic rule set. It tells your system to apply whatever political daylight-saving rules happen to exist at that future moment. If you just store UTC for a human event, you've completely thrown away their intent, and you can never get it back.
All right, Section 5, the golden rules of time. Let's lay out the definitive guide to best practices.
The absolute golden rule for keeping things consistent across your systems is to always store your date and time in UTC using the ISO 8601 format. You've almost certainly seen the string: year, month, day, a T for time, the hours, minutes, seconds, and a Z at the end to denote zero offset, or UTC. Sticking to this format ensures that lexicographical sorting perfectly matches chronological sorting right there in your database.
So if you're building a backend, here is your crucial checklist. First, store physical moments in strict UTC. Second, store future human intents as local time plus the IANA zone ID. Third, do all your conversions to local time purely on the front end. Never rely on the server's local time setting to do your formatting. And finally, make sure your system operators are regularly updating the TZ data database to catch all those sudden geopolitical rule changes we just talked about.
Now, over on the front-end side of things, don't try to guess offsets. Instead, use modern browser APIs. The install.date time format API can reliably detect the user-specific IANA time zone context, like Australia/Sydney. From there, you can use robust libraries like datefens.tz or Luxon to handle all the messy math of daylight-saving transitions securely right there in the user's browser.
Stepping back for a second, the really big picture here is that time isn't just some simple string of text or a ticking integer. It's a critical, highly complex coordinate. Whether you're syncing hardware down to 100 microseconds to keep financial regulators happy, bending your server clock to absorb the Earth's slowing rotation, or just making sure a student in Toronto doesn't miss a deadline in Tokyo, time requires explicit, deliberate architectural management.
Which leaves us with one final, pretty vital question to ask yourself about your own system architecture. Take a look at the dates and times running through your applications right now. Is your database simply storing math? Or is it actually preserving meaning? Think about it. Thanks for joining me on this explainer, and keep building great things.